Hello, my name is Andrew Berg, and I'm presenting the 4,500 seconds small data training approaches for deep drone audio classification. I'm the author, and my co-authors are Dr. Zhang and Dr. Mia Wang. This is presented through the Department of Computer Science and Department of Engineering at the College of Charleston. So why does drone classification matter? There's been recent drone scares, and as the market grows, there's a need for drone analytics and robust classification of unmanned aerial vehicles. As you can see in figure 2, the analytic market is expected to grow as the drone market is also expected to grow. So in this study, we focus on creating a robust UAV audio classification model or models using quality data. A key issue we face in this project is using small amounts of data. It's very difficult to record mass amounts of data for these robust systems. So we focus on 2 deep learning approaches with that in mind. So our tools and environments, we're using Python, obviously, and we containerize an Ubuntu image for running our code on our server. And you can see our specs on the left. It's the CUDA platform. We use PyTorch to model our code, model our deep learning models, and weights and biases was very helpful for tracking all of our experiments and making those public. Other packages that we use were transformers, EFT, and importantly, audio annotations for augmenting the data. For methodology, we used a scaled down 9-class audio dataset. This is scaled down from 31 classes, and we're in the process of recording more classes for future studies. So there are 100 5-second clips for each class, so that's a total of 4,500 seconds. That's the title. So we specifically use this small amount of data to force us to find innovative techniques for training. That being said, our data pipeline takes in a sample, it normalizes and augments it. And keep in mind that augmenting isn't replacing the sample, it's adding to it. Rather, it's adding to the overall data set. So if we augment a data 3 times, then we're going to add 3 more of those. So this inflates the data set heavily, which is really nice for training. From there, we feature extract it, we pass it into our model, and you can see here a MEL spectrogram example visualized. It's really helpful for models to better understand data versus just raw samples. So while we train our CNN or transformer model, we in parallel track it with weights and biases, and this allows us to better have an idea of what's going on under the hood. So for the transformer models, we used a pre-trained model from Hugging Face. We opted for the audio spectrogram transformer, or AST. It's a generalized model that we fine-tuned to fit our dataset. For fine-tuning, we relied heavily on additive adapters. So these freeze the model and they add specific layers that we only train those added layers, which is very interesting and helpful. So for our experiments, we first started with finding the optimal configuration for augmentations. So this was shown in figure 1. For the AST model, we experimented heavily with the adapter types. We found that IA3 was the most consistent and effective. Since the CNN model is much simpler, we only experimented with learning rate and batch size, and we use all those configurations on a 5-fold cross-validated run, which we see is favored to the CNN, which ran much faster and had a much higher accuracy and F1 score. With these preliminary results, we found that the CNN was more effective than the AST model. That being said, there's still much work to be done here, especially as we scale up the data set. It's not known how exactly these models will perform, and perhaps the transformer model could come out on top. If you're interested in the code, you can take a picture of this QR code, or you can open the link below. Thank you.